Hi students, have a nice day. In this section, we are going to discuss about a new concept, enthalpy, a new state function, useful state function, enthalpy. Enthalpy is derived from the term Greek word enthalpy, which means heat content or to heat. Enthalpy is the total energy stored in a chemical system at a constant pressure and temperature. What is enthalpy? The total energy is stored in a chemical system at a constant pressure and temperature is called heat content or enthalpy. It is denoted by the letter H. Okay, it is denoted by the letter H. And H is the sum of the internal energy and pressure volume energy. Okay, what is H? The enthalpy H is equal to internal energy and pressure volume work. Are you clear? Yes. Enthalpy is a state function. What do you mean by state function? You know that the property of a system which depends the state of the system, initial state and final state. So enthalpy is a state function. Also it is an extensive property. What is extensive property? The property which depends upon the quantity or amount of the substance. Okay, it is a state function as well as an extensive property. Okay, so enthalpy is the sum of the internal energy and pressure volume energy at a particular set of conditions. Let's discuss what are the changes in the enthalpy. Okay, so you know that enthalpy H is equal to U plus PV. For finite changes at a constant pressure, okay, finite changes at a constant pressure, we can write that delta H is equal to delta U plus PV by taking a delta on both sides and expanding the equation. Delta H is equal to delta U plus delta of PV, okay, pressure or volume. Delta H is equal to delta U plus delta P into V plus P delta V. As you know that at a constant pressure, delta P is equal to 0. So this term becomes 0. We can write that delta H is equal to delta U plus P delta V. Okay, delta P into V is equal to 0 because at a constant pressure delta P is equal to 0. That's why delta P into V is equal to 0. So this is the change for enthalpy. The change for enthalpy for finite change process. Okay, and also we can explain, we can define the enthalpy change. What is enthalpy change? Enthalpy change is the sum of increase in the internal energy and pressure volume work done. What is P delta V? Work done. Okay, here it is pressure volume energy, here it is work done. Okay, you remember that. So change in enthalpy is defined as the sum of the increase in the internal energy and pressure volume work done. Okay, are you clear? Yes. The next is enthalpy for a exothermic process. Enthalpy is positive for endothermic reaction. Enthalpy is negative for exothermic reaction. Once again, the changes of enthalpy in the exothermic as well as endothermic reaction. Enthalpy change is positive for the reaction involving absorption of heat energy. Okay, enthalpy change is positive, the reaction involving absorption of heat energy, that is a endothermic reaction. Okay, for endothermic reaction delta H is positive. Endothermic. For endothermic reaction delta H is equal to positive. And for exothermic reaction, okay, the reaction involving evolved heat energy, evolution of heat energy, that is for exothermic reaction enthalpy change is negative. For exothermic reactions, the enthalpy change is equal to negative. So let's conclude. For endothermic reaction, delta H is equal to a positive value. Okay, endothermic reaction. For exothermic reaction, delta H, that is change in the enthalpy, is a negative value. Okay, as you know that different enthalpies, ionization enthalpy, electron gain enthalpy, etc., bond enthalpy, etc. In the case of ionization energy, the enthalpy change is always positive because we supply energy. Okay, we supply energy, that's why the system absorbs heat from the surroundings, and that's why ionization enthalpy is a positive value. Electron gain enthalpy. What is electron gain enthalpy? The energy released, okay, when a gaseous isolated atom gains one electron. So when energy is released, the sign of the enthalpy change is negative. That's why we know that the enthalpy, the electron gain enthalpy of chlorine is minus 349 kilojoule. Okay, minus 349 kilojoule. That minus sign indicate that heat is evolved. Okay, heat liberates. That is an exothermic reaction. Then we can discuss some important notes. Okay, for the reaction involving solids and liquids. Okay, for the reaction involving solids and liquids, the volume change is negligible. Delta V is negligible, and that's why the enthalpy change is equal to energy change, internal energy change. Okay, first of all you keep the equation. Delta H is equal to delta U plus P delta V. For solids and liquids, the volume is not important. The volume change is negligible. Okay, there is no appreciable change of volume. In the case of gaseous reaction, the volume changes is appreciable. And first one is for solids and liquids. Solids and liquids, delta V is equal to 0. Volume change is equal to 0. So what about this equation? In such cases, delta H is equal to delta U. Okay, delta H is equal to delta U. Second case, for ideal gas. Okay, for ideal gas, delta H is equal to delta U plus delta nRT. Okay, delta nRT. This is the relationship between the delta H and the delta U. Okay, let's derive what happens in this equation. We know that for ideal gas, PV is equal to nRT. Okay, for ideal gas, PV is equal to nRT. Therefore, P delta V is equal to delta nRT. A very simple relationship. PV is equal to nRT, so P delta V is equal to delta nRT because R is a constant and temperature is constant. So these two are constant and the change happens only for number of moles. So P delta V is equal to delta nRT. What is delta N? Delta N is change in the number of moles of gaseous product minus number of moles of gaseous reactants. That is, delta N is equal to Np minus Nr. Okay, Np minus Nr. And remember that the reactants and product must be in gaseous form. That's why we can write N delta N G. Okay, within bracket G. Here also delta N G of product. P means product. Delta G R. R means reactants. Okay. So this is the second relationship. We can also say that the relationship between change in the enthalpy delta H and a change in internal energy. And the third one, for gaseous reactions in which delta N is equal to 0. Okay, suppose this delta N is equal to 0. Let's take one example. H2 gas plus I2 gas gives 2HI gas. In this case, delta N is equal to number of moles of gaseous products. Here, 2 gaseous products. And number of moles of gaseous reactants. 1 plus 1, 2. So here, delta N is equal to 0. Delta N is equal to 0, and in this case, if delta N is equal to 0, delta H is equal to delta U. So for gaseous reaction in which delta N is equal to 0, the delta H is equal to delta U. Okay, are you clear? Yes. Then another some examples. If the reactants and the products are in the gaseous state, reactants and the product in the gaseous state, we consider some reactions. First one, okay. First one, 2SO2 plus O2 gives 2SO3. All are gaseous states. All are in the gaseous state. Whatever the delta N? Delta N is equal to 2. 2 minus 3. Okay. 2 plus 1, 3. 2 minus 3. That is minus 1. Here, the change in the number of moles is negative 1. And the equation, according to the change in enthalpy, delta H is equal to delta U plus delta N is minus 1. Minus 1 RT. That is delta U minus RT. Delta H is equal to delta U minus RT. And here delta H is less than delta U. Delta H is less than delta U. And in the case of another equation, 2NH3 gives 3H2 plus N2. What is the change in number of moles? What is delta N? Delta N is equal to 3 plus 1, 4. 4 minus 2. Here the change in number of moles is equal to 2. The change in number of moles, that is delta N is equal to 2. That is, delta N is positive. So, delta H is equal to delta U plus 2 into RT. That is, delta U plus 2 RT. Delta H is equal to delta U plus 2 RT. Here, delta H is greater than delta U. Okay. So, when delta N is equal to 0, delta H is equal to delta U. Where the delta N is negative value, delta H becomes less than delta U. And delta N is positive value, delta H is greater than delta U. Okay, clear? Yes, next we discuss the relationship between delta H and delta U. Already we know that delta H is equal to delta U plus P delta V. Okay, delta H is equal to delta U plus P delta V. From that we derive a relationship between delta H and delta U. Delta H is equal to delta U plus delta nRT. Up to this we derived. Then we discuss another relationship. Okay. Remember that delta H is QP. Okay, delta H is QP and delta U is QV. Delta H is the heat content at a constant pressure and temperature. You know that. So delta H can be written as QP and delta U becomes QV. Okay, already discussed this. Delta U is equal to heat absorbed at a constant volume plus delta nRT. Okay, another equation. If delta N is equal to 0, QP is equal to QV, isn't it? Suppose this delta N is equal to 0. 0 into RT 0, then QP is equal to QV. Another relationship. So we have three relationships between the delta H and the delta U. One is delta H is equal to delta U plus P delta V. Another equation. Delta H is equal to delta U plus delta nRT, where delta N is difference between number of gaseous products and number of gaseous reactants. Okay. Then delta H is QP, heat absorbed or liberated at a constant pressure and constant temperature is QP. Then delta U, as earlier we derived, delta U is equal to QV. Then delta nRT. Okay, then last one, if delta N is equal to 0 for gaseous reaction, suppose delta N is equal to 0, QP is equal to QV. Okay, then another is measurement of delta H, the measurement of change in enthalpy. The change in enthalpy is determined by an ordinary calorimeter. Change in enthalpy is determined by using an ordinary calorimeter. The substance is taken in a calorimeter and this is immersed in a water. Okay, immersed in water. And the temperature of the system, the temperature of the calorimeter before or after the reaction, before and after the reaction is taken, note down, and the change between the two temperatures is delta T. Okay, the change is delta T. By knowing the delta T, we can easily determine the enthalpy change of the reaction. How? QP is equal to C. What is C? C is the heat capacity of the calorimeter minus C delta T M divided by small m. What is capital M? Molar mass of the substance, and small m is the mass of the substance taken. So ordinary calorimeter is used to determine the enthalpy change of a reaction. And remember that bomb calorimeter is used to determine the internal energy change. Okay, internal energy change is determined by using bomb calorimeter. Delta H is determined by the ordinary calorimeter. Let's discuss some problems based on the internal energy change and work done. First question. A system absorbs 800 kilojoule of heat and does a work of 250 kilojoule. Calculate the change in the internal energy. Okay, the question is once again, a system absorbs 800 kilojoule of heat and does a work of 250 kilojoule. Calculate the change in the internal energy. The question is based on the internal energy change and the heat absorption. So here the system absorbs 800 kilojoule of heat. Absorbs means positive side. Okay, you know that when the system absorbs heat energy, it is positive side. When the system liberates heat, it is negative side. And also does the work. That means the system do work. That's why we put the minus side. Minus 250 kilojoule. This data is given. Okay. Q is equal to 800 kilojoule and W is equal to minus 250 kilojoule. Why? The system do the work. Okay. The system do the work. Work done by the system. That's why minus W. According to first law, we know that delta U is equal to Q plus W. A very simple problem. Q is 800 kilojoule and W is minus 250 kilojoule. What is the difference? It is 550 kilojoule. What is the internal energy change in that process? It is 550 kilojoule energy. Okay. And the second question. A sample of gas undergoes expansion against a pressure of 1 atm from a volume of 500 milliliter to 906 milliliter by absorbing 500 joule of heat. Calculate the change in the internal energy. Once again, I read the question. A sample of gas undergoes expansion against a pressure of 1 atm from a volume of 500 milliliter to 906 milliliter by absorbing 500 joule of heat. Calculate the change in the internal energy. Okay, first of all, we have to collect the data given. Pressure P is given. P is equal to 1 atm. And volume, initial volume V1 is equal to 500 milliliter. Final volume V2 is equal to 906 milliliter. Okay. And the change in volume delta V is equal to 906 minus 500 milliliter. What about the change? It is 406. Okay, it is 406 milliliter. We can written in the liters. Okay, it is 0.406 liters. Okay, usually we are doing in liters. And another important information is the system absorbs 500 joule of energy, that is plus. The system absorbs 500 joule of energy. And the question is change in the internal energy. What is internal energy? Delta U. It is Q plus W. Okay, Q plus W. Then Q is 500 joule. 500 joule. And expansion work. Expansion work means work done by the system. That's why the W is negative. Okay, the W is negative. Then W is P delta V. Okay, W is equal to P delta V. Then substitute the values of pressure and change in the volume. What about this? It is 500 joule minus pressure 1 atm into volume change 0.406 liters. Then it is 500 joule minus 0.406 liter atm. Okay, 406 liter atm. And the problem is, here the unit is joule, here the unit is liter atm or atmosphere liter. One hint is given, 1 liter atm is equal to 101.3 joule, or you can write that 1 atm liter. Okay, 1 atm liter is equal to 101.3 joule. Multiply here. Okay, 500 joule minus 0.406 into 101.3 joule. Now it is in joule. Okay, 1 liter atm is equal to 101.3 joule. What is the value? 500 joule minus, the answer is 41 point. By multiplying this, 41.13 joule. And the final answer is equal to 458.9 joule. Okay, rounding off. Actually it is 87, round off into, okay, write correct value, 87 joule. So this is the internal energy change for this process. Once again, the given data, okay, the given data is pressure 1 atm, okay, pressure 1 atm, volume 500 milliliter changes into 906 milliliter. What is the change? It is 406 milliliter. Milliliter is converted into liters by dividing 1000. So 0.406 liter. Then Q is given 500 joule energy absorbed, that means positive sign. And according to first law of thermodynamics, delta U is equal to Q plus W. 500 joule, Q is equal to 500 joule, W is equal to, W is expansion work, that is minus P delta V. Okay, minus P delta V. By substituting the values, we get 500 joule minus 180 into 0.406 liters. Then 500 joule minus 0.406 liter atm. Different unit. Here joule, here liter atm. To convert liter atm into joule, this is the multiplication factor. 101.3 joule. Multiply it, we get 41.13 joule. By subtracting, finally the delta U is equal to 458.87 joule. Okay. Then we move to the next problem. When certain amount of gas is heated at a constant volume, 627.5 joule of heat was absorbed. Calculate the change in the internal energy. Okay, the third problem. When certain amount of gas is heated at a constant volume. Constant volume means delta V is equal to constant. Okay, delta V becomes constant. 627.5 joule of heat was absorbed. 627.5 joule of heat was absorbed. Calculate the change in the internal energy. Okay, here the gas is heated. Gas is heated at a constant volume. That is delta V is equal to 0. At a constant volume means delta V is equal to 0. Another important thing, the heat energy absorbed is equal to 627.5 joule. Okay, these are the data given. Calculate the internal energy change. Okay, it is expansion work W is equal to P delta V. Okay, a certain amount of gas is heated at a constant volume, 627.5 joule of heat absorbed. Then W is equal to P delta V. At constant volume, minus P into 0. Delta V is equal to 0. So what is the work? Work is equal to 0. Work done by the system is 0. Okay, work done by the system is 0. Then according to first law of thermodynamics, delta U is equal to Q plus W. Delta U is equal to Q plus W. So delta U is equal to 627.5 joule plus 0. Q is equal to 627.5 joule plus 0. Here delta U is equal to the heat absorbed by the system to 627.5 joule. As we already discussed, delta U is equal to QE. What this V denotes? The V denote delta V is equal to 0 at a constant volume. Already we discussed. That's why I told you memorize equations. Okay, now need to memorize the derivations. You memorize the different equations because that equation is applicable in questions. Okay, the application of equations in the question. So here we know that delta V is equal to 0, delta U is equal to QV. The heat absorbed by the system. We prove that if W is equal to 0, delta U is equal to the Q, that is the heat absorbed by the system. That's about the problems based on the internal energy and the work done. The problems based on the enthalpy change we will discuss in the next section, because before we are doing the problems we have to know about the different enthalpies: enthalpy of reaction, enthalpy of vaporization, enthalpy of combustion, enthalpy of fusion, like that. So we will see more about the enthalpies in the next section. Thank you.